Yeah.
No problem. Hi, everyone, and welcome to our Connecting with Professionals series with Robotics Team High Definition and Professor Crowder. And she is a physics professor at Bellevue College, and she's done so many cool studies, including with launching a rocket, searching for remnants on the early universe, studying hot gases in space, traveling deep underground, and today she's going to be talking about her studies with gravitational waves. And at the end of the presentation, you're going to be welcome to ask any questions of anything about her bio, or you can ask about gravitational waves, what she studies, physics, and anything else you'd like to ask our expert. So I'm going to hand it over to Professor to get started.
Thank you very much, Isha. So as Isha said, today I'll be talking about my work with gravitational waves, but if people have questions about any of the other things I mentioned in my bio, I'm happy to talk about them afterwards in the questions. So I'm going to talk about gravitational waves, and gravitational waves are actually they're a way of energy traveling, but it's a very weak mechanism. So we have to look at some of the most energetic and massive events in the universe to even hear a whisper from these gravitational waves. So Isha, would you go to the next slide, please? So outlining what I'll be talking about today, I'll talk about what gravitational waves are, why they're important. I'm going to talk about some of the early attempts at trying to detect them, as well as the recent detection that's been made with the LIGO Laser Interferometer Gravitational Wave Observatory. And I'm going to talk about why that's exciting in terms of gravitational wave astronomy. Next slide, please. Okay, so astronomy is actually the oldest of the natural sciences. When we think about astronomy these days, we sort of think, oh, it's really cool, gee whiz, space age. But astronomy actually, when it was originally practiced, was a very practical science. People used it for things like timekeeping, sun rising in the morning, setting at night, day and night, also seasonal, when to plant crops, but also things like navigation. People looked at the North Star to know directions, and east and west with the rising and setting sun. So it really has a long history of being a very practical science, and it's been practiced for thousands and thousands of years. For all of those thousands of years, it has been practiced by people looking up at the sky. So if you had good vision, you could see the stars or whatever you're looking at very clearly. If you're someone like me who has glasses, you probably couldn't see as much as what's going on up there. So for all these thousands of years, it was sort of limited by the people with the very best vision and what they could see of the sky. So it had to do a lot with what our eyes are sensitive to. So at the top of this slide, there's that sort of rainbow section there that's labeled visible light, and that's what our eyes are sensitive to. And you can see it's part of a much larger band of what's all light, or sometimes called electromagnetic radiation. And it's all the same kind of thing. It's just sort of, you think of light as a wave. Some of that wave is more sort of stretched out like a radio wave, or some of it's more squished together like an X-ray or a gamma ray. Okay, so for the thousands of years that astronomy has been practiced, it has been visible light that we're looking at, and it's just coming from what we can see with our eye. Now, astronomy is very information-limited science. We're sort of having to scramble about every little photon of light we can get to get information. So you can imagine you put in the 1600s, the telescope was invented. And within a year of that, people started pointing the telescope up at the sky, the night sky, to see what was going on. And the reason this was so important was because when they looked up, it still did the same thing your eye did. It just sort of captured more light than our eyes do. So we got more information, and we were able to see a lot better what was going on up in space. So kind of discoveries that happened when people looked at the sky with a telescope as they saw the moons of Jupiter for the first time. Now, for us, that might sound cool, but not so exciting. But you have to realize at this time, people realized that there were other planets, and they realized we had a moon, but they had no idea that other planets could have their own moons. So it really changed the mindset of how people understood what was going on in space just by getting a little bit more information. So then people tried, the race was on to build better and better telescopes to look at visible light in the sky. And that continued until maybe roughly 70 years ago, maybe a little bit longer. And people said, well, how about we look for other kinds of light in the sky, not just visible light? So if you look at the bottom left-hand corner, there's a picture there of a radio telescope. It's an array of telescopes there. That's the Very Large Array in New Mexico. And it looks for radio waves from space. And when they started looking for radio waves, they made all sorts of new discoveries. They discovered things like pulsars and quasars and radio galaxies. In the lower right-hand corner, we have an X-ray telescope called New Star. You can see that's in space because X-rays don't make it through the atmosphere. When people started looking in space for X-rays, they discovered things like X-ray binaries or active galactic nuclei. So just by looking and seeing different types of information, all the different kinds of light, we got totally new conception of all the things that are going on in space. So everything I'm talking about so far, though, is all different kinds of light. So would you go to the next slide, please, Isha? So what I'm going to be talking about today actually is not having to do with light at all. It's a completely new way to look at the sky. It's looking at the sky for gravitational waves, which are not light. And I'll talk more about what it is in just a minute. So one of the reasons it's so exciting is because of all the potential for totally new discovery that comes with this kind of new way of observing the sky. The first observation of gravitational waves was made in 2015, I believe. And so you can see artists' visualization of it in the upper left-hand corner. There are some two black holes that were orbiting around each other, getting closer and closer to each other until they finally merged into a single black hole. And that process released gravitational waves, and we were able to observe that here on Earth. Since then, there have been more observations that have made with gravitational waves. On the right-hand side, you see an artist's rendition of two neutron stars that spun around each other until they collapsed into a single object. And that picture in the bottom in the middle is a black hole and a neutron star colliding until they became one. So these are sorts of things that we just never could get information on before because we didn't have gravitational waves. Next slide, please. Okay, so that gives you a little idea of some of the excitement around the gravitational waves, but let's go back to the beginning of the story, which really has to do with Einstein. In 1915, Einstein published his general theory of relativity, which you probably have heard about. At the time it was published, people read it and they thought, wow, this is really cool, but seems totally, totally impractical. There were some different predictions he made within his paper, and people were able to test these pretty quickly, many of them, and there were several confirmations for it, but people didn't think it was going to be useful. But if you fast forward today, it's become so important that our phones wouldn't work unless we took into account general relativity because of the GPS in there having to communicate with the satellites. So just by the scientific innovation, just trying to pursue what's interesting, things end up becoming sort of important later on in ways we can't imagine initially. One of the things Einstein predicted with his theory was that a byproduct of his theory is that gravitational waves would be created. So that some energy would be carried away from certain kinds of events in the fabric of space-time. And at the time he did this, he said, I include this here for completeness, but it's such a tiny effect, it's not possible to observe it. And from Einstein's point of view, with the technology of about 100 years ago, it's true, it was totally impossible to imagine making this kind of observation. But if you fast forward 100 years later with a lot of hard work and innovations, we're at the point where we're able to make this discovery. Next slide, please. So general relativity is a theory that talks about the interactions of matter, and it's called space-time. So there's this famous quote by a physicist, John Wheeler, that says, matter tells space-time how to curve, and curved space-time tells matter how to move. So if you imagine you have a tarp, a stretchy tarp that's stretched flat, and on it you put something heavy, you can imagine that, let's say there's a bowling ball you put in it. The bowling ball is going to cause that tarp to dip in the center. So think of that space-time being stretched by something with a lot of mass. Something smaller like a tennis ball on the tarp would just make it bend down a little bit. So the big masses make space-time curve more. And if you can imagine, if you look at this picture here, you can see there's this grid on there. if you sent like a little satellite traveling along one of these straight lines and it happened to go close to the sun, you could see that it goes along this part where the space-time is curved. And so the matter travels along that straight line. Next slide, please. So, as I started talking about at the beginning, almost all of our astronomy knowledge to date is coming from light. And light is made by having an accelerating charge. Okay? And there's some really good things about it, which is that it's, in general, it's easy to make light, it's easy to detect it. So, you know, you can light a match or turn on your flashlight or anything like that, make light very easily. We've got a lot of ways to do that. It's easy for us to detect it with our eyes, lots of other detectors out there, which is great, right? We can get a lot of information from light. But a downside to it is it's also easy to obscure. So I'll give an example here on this picture on the left. This is an image taken by NASA of what's called the pillars of creation. And this is actually a star-forming region. So you see these sort of tall vertical structures here. Those are dust clouds. Okay, so in the picture, those look like they're kind of dark. But inside those clouds is actually a star-forming region. So there's lots of stars that are starting to ignite and release a lot of light there. But we can't see those stars inside because there's all that dust in the way that blocks that light. So there's a lot of information there, but there's certain places we just can't see with light. Next slide, please. Now, gravitational waves are, instead of coming from an accelerating charge, instead come from any accelerating mass, which, in general, it's hard to make them, and it's also hard to detect them. However, flip side is it's also really hard to block them. So if you're able to see them, you can see to places, or you can get information from places that you wouldn't be able to get information with light. Next slide, please. So think of gravitational waves as ripples in this fabric of space-time. Okay, and if we wanted to measure the size of those ripples, we'd talk about measuring the amplitude, and the special word we have for that is called strain. And it has to do how the fractional change in the length. So you see on the left-hand side there's a circle. Imagine you have a circle of little test particles, and you're out in space. And imagine a gravitational wave came and it went straight into the screen, right through that circle of test particles. What would happen to the shape of those test particles is over time, they'd squish in one direction and stretch in the other. They'd go back to the circle, they'd stretch in the other direction and squish in the other direction before going back. So please advance one slide. So here, this gives you an idea as if a gravitational wave went through the screen, what would happen to the particles that were there. Next slide, please. Okay, so we've got these gravitational waves. How big an effect are they? Next slide, please. So let's imagine here we've got an angry motorist and he's shaking his fist. Okay, right? His fist has some mass, so there's got to be some gravitational waves from them. So if you went ahead and you calculated the amplitude of his fist moving around, so remember we measure that in terms of strain, that value of h, it's going to be something times 10 to the minus 52. So a teeny, 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 tiny fractional length change. Okay, so not possible for us to detect these days. So you might say, okay, that's somebody's fist. We don't expect to be able to detect something like that. What about something bigger? So please advance the slide. So instead, take two warships that collide into each other, right? That's a lot more mass that's colliding. And indeed, that's a 1,000,000 times stronger effect, but still, something times 10 to the minus 46 is a teeny, teeny, tiny amount. Next slide, please. So you may say, okay, forget things just on Earth. Let's go nearby. Let's say Jupiter and one of its moons moving around it. Okay, so now this is a lot bigger effect. It's a 1,000,000,000,000 billion times bigger than the warships colliding. But we still are trying to look at something where its fractional change in length is 10 to the minus 25. Very, very small, not within our ability right now. Next slide, please. So let's say we take the loudest possible source we can think of in the galaxy, which is imagine you've got some neutron stars They're spinning in, about to collide with one another, okay, and they happen to be nearby us in the galaxy. That fractional change in length is 1,000,000 times stronger than what we might see with Jupiter and its moon, okay, and it's still teeny, teeny, tiny. It's a fractional part of 1 in 10 to the minus 19, okay. Next slide, please. So if we were going to try to detect that, if it's a fractional change of length, that means we need to figure out what size our detectors are. So let's just say our detectors are 1 kilometer long, okay? That means the motion that we're looking for in the detector is 10 to the minus 16 meters. It's smaller. We're looking for a change in length that's smaller than the width of a proton. Now we've observation, right? But I want you to appreciate what a tiny measurement that was and how amazing that this has been done. Next slide, please. Okay, so why are something that's so small, why is it so important? Well, one reason is it's a confirmation of general relativity, right? There's this theory out there, there are lots of predictions, we want to check all of those. However, there have been lots of checks of general relativity, so it's not so surprising that it passed another one of its tests. I think what's most exciting about the promise of gravitational waves is it's a new tool for studying the universe. It's a totally new source of information. So we can study things that we weren't able, study them in a way that we weren't able to study them before. So I've talked about examples like black holes and neutron stars spinning until they become a single object. We've made observations of those. There's some other things that we haven't seen yet, but we expect to make gravitational waves, like spinning neutron stars, or if you had things like supernovas, or things that are going on in the very early universe as well. Plus, there's potential to discover totally new sources of gravitational waves, of things we haven't even imagined before. Next slide, please. So remember, Einstein came up with his theory in 1915, and for about 50 years, roughly, nobody tried to do anything about it because it just seemed impossible. And then sometime around the 1960s, the person pictured here, Joseph Weber, decided to try to look for gravitational waves. And he was a serious scientist, a real scientist, and was well respected, but he was the very first one that tried to do that. Isha, I'm not seeing the slides anymore. Nor am I seeing Isha. Okay, perhaps she will join on, but I will keep talking for the time being without showing the slides. So what Joseph Weber did is he went through, and I don't know if you remember the picture that was up just a moment ago. His detector was really a great big cylinder of metal. And what was supposed to happen is a gravitational wave would come through and make it resonate, vibrate, and it's a resonant frequency, and he'd be able to detect that to find the gravitational wave. What happened though is he thought he made a detection. He thought he made an observation. However, other people went to try to reproduce his results, and they were not able to reproduce his results. So even though he wasn't fabricating data, he honestly thought, he went to his grave thinking he detected gravitational waves, but no one else could find it. In hindsight, he probably didn't. It was probably something instrumental he didn't understand. But it was really important that he did this, because then other people started trying to look for gravitational waves, and other people started going through and finding, carrying on his search. And they used other ways. Next slide, please. So the next update comes in the 70s, and this was an indirect detection where people were using the Arecibo radio telescope that's shown in the left-hand picture. And what they were doing is they were looking at some neutron stars that were orbiting around one another. And they were looking for signs how long it took those neutron stars to orbit around each other. So you can imagine if you have normal kind of physics, like when I say normal, I mean your everyday living on Earth kind of physics, Newtonian physics, that you'd imagine the time it takes for things to orbit are the same. So if you looked at the difference in how long it takes to orbit, it would be 0. You wouldn't imagine it to change at all. So if we look at this graph on the right-hand side, it's graphing how much the change in that orbit time is as a function of the observation. So there's that horizontal line at 0 there. That's what you'd expect if you had regular Newtonian gravity. However, that's not what they observed. You can see that there's some data points there that fall further and further away from that line, meaning that it takes less and less time for those two neutron stars to orbit around one another. And if you look at the line that passes through those points, that's actually the prediction from general relativity. So they have indirect but very strong evidence for gravitational waves. Next slide, please. So what I'll be talking mainly about today is a new type of detector which directly detects gravitational waves, called LIGO, for Laser Interferometer Gravitational Wave Observatory. So you can see why we call it LIGO for short. So the LIGO detector is looking for, you can think of it as an observatory, looking for totally new sources out there of gravitational waves from the sky. It's a very big collaboration with over 1,000 scientists worldwide. And there are a few different sites for it. In the lower left-hand picture, you can actually see that one of the LIGO sites that's here in Washington State. It's near Richland, Washington. Sometimes they offer tours. You might have to check ahead now with the pandemic, but you can go and visit this place. There is another site that's in Louisiana, here in the middle. On the right-hand side in the bottom, it's not LIGO, but a sister collaboration with whom we share data. It's called Virgo. It's in Italy. Above that is a detector is being built underground in Japan. It's known as Kagra. And then there's another one that will come online a little after that, will be in India as well. So lots of different great sources. We can work together to get the best data as possible. Why don't you go forward 2 slides, please? So remember I talked before when we were talking about what happens when a gravitational wave passes by, and I talked about the circle of test masses and how they squish in a certain direction and stretch in the other. So the way the detectors work with LIGO is instead of having a full circle of test masses, we've got 2 test masses, which are mirrors, and they're at 2 sides of the circle that's sort of perpendicular from each other. So we have some laser light that comes in, gets split into 2 paths, and we measure the time it takes to go down those 2 paths. And we see the difference in those mirror distances over time. Next slide, please. So here is a sort of a simplified view of how the interferometer works and how it is that we're able to measure a change in length that's something that's less than the width of a proton. Are you able to start this video, Isha? So some light comes through, bounces off the mirrors, goes through, and then we see as those mirrors move around, because if there's a gravitational wave, it causes this flickering pattern on that square detector right there. So there's the light coming through with the wavelength that's split at the beam splitter. Some of the light goes along here. It takes some amount of time. It bounces off the mirror at the end. The other light is doing that the other side. It's recombined at the beam splitter, and then we've got our light going through to that square detector on the right-hand side. Right now, the light is sort of anti-aligned. It's constructive interference, so there's no light. When it's aligned, you have constructive interference. So what we're looking for is this characteristic flickering pattern. So we can go to the next slide. So that was a simplified view of the detector. And this is actually a simplified schematic as well, but it's just to let you know that there's actually a lot more that we have to go on, a lot of tricks we have to use to be sensitive enough to such small differences in length. Next slide, please. So what were we able to do with this? So the very first detection with LIGO was the very first direct detection of gravitational waves. And what we detected was two black holes that were orbiting one another. It was the very first time that we ever saw black holes orbiting one another. It was also the first detection of black holes merging into one. This was an event that occurred over 1 billion years ago, and those gravitational waves were traveling for 1 billion years until they just happened to wash past Earth at a time we were looking. The black holes that went into this collision, one of them had a mass about 29 times the mass of the sun. The other one had mass about 36 times the sun. And they merged into a single black hole that was 62 times the mass of the sun. So you may say that, hey, 29 plus 36 does not give you 62. It gives you something bigger, which is exactly right. If you think about E equals mc squared, some of that mass from those black holes was converted to energy and was carried away by gravitational waves. On the left-hand side here, we can see the actual graphs. So you can see with your eyes what we detected for the gravitational waves. The top panel here shows the strain. Remember, that strain is how we measure the amplitude of our gravitational waves. So it shows the strain here as a function of how long we've been detecting. So this whole thing happened in less than half a second. The top panel shows the data from our detector here in Washington at Hanford. The middle panel shows our detection from Livingston, Louisiana. The bottom panel shows them just graphed on top of each other. You can see what a good match there is between those separate sites. Next slide, please. Okay, so let's try to imagine what went on at the time of that gravitational merge of two black holes. So here is an artist rendition, a simulation actually. So you can see in the middle here, there are two black spots, which are meant to represent two black holes. And then there are some stars in the background. So what you can imagine is, imagine we all hopped in a spaceship and we flew our spaceship to be close enough so that we could watch, but we weren't like pulled in and collapsed into the black hole. So will you please start the video, Isha? So what you'll see is those two black holes are rotating around each other, and you see the light that's moving around in the outside. And that's because, remember, that a gravitational, things with big mass bend the path that the light takes from general relativity. So we're seeing right now, if you look sort of on the edge, there's a little bit of a ripple around it as you get further from the edge. And that little ripple on the edge is the gravitational wave. And here we have our single black hole now, so then there aren't really any gravitational waves that are being made anymore. Next slide, please. Okay, so here's another simulation. This one might be a little bit hard to see unless you've got a nice dark room to look at it. But let's imagine those gravitational waves were made, they are traveled for the 1 billion years, and then they happen to be passing nearby when we're looking for it. Let's imagine what happens on Earth. And I should say this is greatly, greatly, greatly exaggerated, just so you get a feel for like what's going on. Okay, so what's going to happen is on the lower right-hand side of the screen, you're going to see these kind of like pale yellow clouds that are drifting towards the up left side of the screen. Those are the gravitational waves. As they get bigger, the gravitational waves are getting bigger. So go ahead and start the video, please. So there's the first one. You can see a little bit of a ripple of the Earth. So that gravitational wave goes through, and you get, as those two black holes are getting closer and closer to each other, you get more and more intensity, you get more of this rippling. It's like a big bowl of jelly, and then it passes by, those gravitational waves keep traveling, and we've made our detection, but otherwise the Earth is fine, right? It doesn't really ripple as big, it's much, much smaller effect than that. Next slide, please. So this was important enough work that in 2017, these three people won the Nobel Prize in Physics for this work. These three people, Ray Weiss, Barry Barish, and Kip Thorne, were real founders and innovators in getting instrumental into getting LIGO working and making sure, fostering it along its path. But keep in mind, it is a collaboration of over 1,000 people contributing to make this happen. Next slide, please. Since then, there have been more detections than that, just showing the sort of the promise of gravitational wave astronomy. We have detected neutron stars colliding And something that was so exciting about the neutron stars, that was different from the black holes. Black holes, we didn't expect any light to be coming from them, so other telescopes that use light weren't able to detect anything. However, with neutron stars colliding, we can see things using normal light mechanisms. So you can imagine here that we had, with this detection, we had 3 gravitational wave detectors. We had 70 ground and 7 space-based light observatories. The entire electromagnetic spectrum were able to observe this event. So because we had this observation using gravitational waves, we're able to figure out that it was neutron stars colliding. Without LIGO taking this detection, they didn't know that it was neutron stars colliding. So what would have been thought before this detection with gravitational waves is something that's just called a gamma ray burst, because people don't know what causes them. They happen all over the sky. So with essentially getting this really important puzzle piece, they're able to change what was called a gamma ray burst into something that's an off-axis neutron star collision. So that was really exciting. Plus, it was the first experimental evidence of what makes a large amount of some of the precious metals that we see in the universe. So if you're wearing some metal jewelry now, like a gold necklace or a ring or something like that, you may have something that was born in a neutron star collision. So one of the things that's so exciting about this is it's a brand new way to look at the bright and the dark universe. Next slide, please. Since then, there have been a lot more detections of both black holes colliding into a single black hole, also some neutron stars colliding, neutron star and a black hole. So you can see we're getting lots more information and filling in a lot of more of the picture of what's going on out in space. Next slide, please. And I just want you to keep in mind, this is a very exciting time. It's really the birth of gravitational wave astronomy. On the right-hand side, that column of pictures, the bottom picture there, that's the LIGO detector here in Washington. But just like with gravitational waves, how we had visible light, and we had radio waves, and we had X-rays, and studying those different areas gave us lots of information, we can do the same thing with gravitational waves as well. If we look at different frequencies, we have the possibility to learn about totally different mechanisms that are going on out in space. Next slide, please. So in case you're interested, I've attached here a few other resources for you to look into. There's a video called What are Gravitational Waves? It's a good introductory video. There are what are called the GWOSC learning paths. So all sorts of things you can do there to practice online skills, figuring out the mass and distance of colliding black holes, a lot more on there. There's an online game called the Black Hole Hunter. And then there's also a citizen science project called Gravity Spy, where you help classify glitches in real LIGO data. So if you're interested in any of those, please take a look. If you have any questions you'd like me to ask me about either gravitational waves, my role in them, anything about the other things I talked about in my bio, like going to Antarctica or launching rockets, I'm happy to answer those now. But thank you very much.
And thanks so much for talking about the subject. So if anyone has any questions, feel free to put it in the YouTube live stream chat. But until we get some, I'll just ask some of my own. So what really got you started in physics?
That's a great question. When I was in high school, I was preparing to go off to college, and I was trying to decide, figured I should at least start with a plan, even if I decided to change it. And I was a person, I really liked a lot of different topics. Some of them were in science and math, and some of them were totally, like humanities topics. I didn't feel like I knew for sure where I wanted to go. But I did know that I remembered when I was a young child, I really enjoyed looking up at the night sky and imagining what was going on there. And so I thought, well, maybe I'll try astronomy. The college I went to did not have an astronomy major, but physics is very closely related. So I went into physics, and then I ended up staying with physics. And I found along the way that physics, there are a lot of challenges, but one of the things that ended up being made a big difference for me is when I was there, I talked to my advisor, who wasn't a science advisor in particular, but just she happened to know. She said, you should try to join a research group. So she gave me somebody's name that she knew. I went to him. He didn't have any jobs. He suggested me to somebody else who did not have any jobs, but I just asked. And finally, I found somebody who was offering a job. I worked in that lab for about a year. I was really enjoying it. It gave a lot of context to my classes and just made them very realistic. And I understood what the sort of like life of a physicist would be a lot better working in that lab. Furthermore, after a year, I found out that this particular experiment, which was studying microwaves from the early universe, was studying that by sending up a scientific balloon in Antarctica. So just joking around, I said, hey, I don't suppose you need someone else to go along? And they said, sure, you can come along. So that I was able to go and take part in that experience down in Antarctica. And then doing that really motivated me in terms of going to grad school. And that's where in grad school I did work with X-rays from space. And X-rays are absorbed by the atmosphere, so you have to go above them. So that's why we launched our instruments aboard rockets to get above that. And then from there, I went on to a position where I was working with gravitational waves.
Wow, that's fascinating. What types of things did you do in high school to get you to those interests in astronomy and soon to be physics?
I think if you're somebody who's interested in the sciences and math, I mean, certainly you should be taking science and math classes in high school and taking them seriously. I was very much, do things that interest you, things that you're going to learn from, but like stuff you want to learn and you want to do. So I'd say do that and then be open to new opportunities. I wasn't, to go to Antarctica, I had to take a year off college, which was certainly not in my plan, but it was definitely worth it to go and have this year doing research. So I'd say be flexible to opportunities that are out there.
Yeah, it's like that's amazing. I know that I'm personally interested in science, so I'm going to take your advice and start probably taking more science courses.
Great. Yeah, definitely check into it. Anything you think is interesting, just follow up on that interest.
Yeah, so what keeps you interested in physics?
Well, I really like the mindset, the problem-solving mindset. I find very satisfying. So it matches the way I think. Also, I like my position now. I do some research, but I also work with students, and so I like that quite a bit. It always, things are always different and changing. Every student is different, so I enjoy that quite a bit. And so, keeping currency, paying attention to what's going on, just talking with other people is a great way to keep that interest up.
Yeah, definitely. I totally agree. Like as a student, I like to stay current in what I'm interested in.
Mm-hmm.
So I know that for high schoolers like me, when they encounter physics, they're like math, and they don't want to do physics because of that. So what would you say to these types of students?
I would say, physics can be challenging, but I think it's like that for everybody, right? So if you're somebody who likes to enjoy like solving puzzles and figuring things out, it can be a good match. I think if you find it challenging, it doesn't mean there's anything wrong with you. It's just a chance, an opportunity to learn. So I'd say approach it with that mindset of it's a chance to learn something new, and it's you get to learn a lot of cool stuff about what's going on in the universe.
Yeah, interesting. Yeah, I know that a lot of my friends see physics as math, so I think that's really quite interesting. How like when you're talking about how this is also applied to astronomy, that really got me interested.
Yeah, there are a lot of great other fields one can go into from physics. So, of course, astronomy, engineering, geology, in geophysics. There are a lot of environmental sciences. So it's a lot of places. A physics degree can be very general. You can branch into a lot of different areas. Then if you graduate, there are opportunities if you wanted to keep, say, teaching or doing something like researching, you can do that. There are a lot of physicists, once they get their degree, go into industry. There are a lot of really interesting industry, creating different kinds of machinery, or, I don't even know all of it. There's a lot of really cool jobs that you can get as a physicist.
Wow, that's so cool. So you mentioned in your bio that you went to South Dakota to travel deep underground to study these gravitational waves. So how does that study connect to what you talked about today?
Yes. So that part wasn't in today's talk. So to go under, that was planning to build a future gravitational wave observatory. So the current LIGO detector is built on the surface of the Earth, but there's some seismic motions that makes it so where it limits the sensitivity of the LIGO detectors currently. So for a future detector, one option is to try to build the same kind of idea for a detector, but have it be underground instead, where it's quieter. So I was going underground in South Dakota to study the seismic environment and see how suitable that would be for a future gravitational wave observatory.
That's great. Very interesting studies that you do. Is there anything that you would like to say to a high schooler with your experience teaching physics at Bellevue College?
For a student interested in teaching? Is that what you're asking?
Just for a student interested in going to physics.
Oh yeah, I would just say stick with it. Things can be frustrating for everybody at certain points. Stick with it. Form study groups. Don't be afraid to talk to your teachers and go to office hours and ask questions. Really, just think if you have questions, you make mistakes, it's an opportunity to learn. And people are there to help. Teachers are there to help you. So really take advantage of that.
Great. Yeah, I personally, I definitely will take that advice, and I hope that others listening to this live stream will do so as well. Do you have any goals for the future now that you've done all these studies, you are keeping current with physics, you're a professor? Is there anything that you want to accomplish?
Well, I'm continuing to do the research, and that always changes gradually over time. So right now, LIGO is still taking data in different observing runs, and so I'm participating in that. At a certain point, LIGO will complete in its particular version, and then at which point I'll probably move on to future gravitational wave observatories while continuing my teaching.
That's great. So you plan to stay in the gravitational waves field?
Yeah, I think for now it works well. There are, of course, a lot of other interesting things out there. And like I said, I always like to keep open to possibilities. But for right now, there's a lot of really exciting stuff going on in the field.
Yeah, that's so interesting. I'm very fascinated by what you've been talking about today with your research.
Well, thank you for having me. It was a pleasure talking with you.
Yeah. Thanks for coming on the show. So if anyone has any other questions they would like to ask our guest here, please put it in the YouTube live stream chat. Otherwise, we would like to thank you for coming and have a great day.
Thank you very much. Have a great day.
You too. Bye.
Bye-bye.
So thanks everyone for coming to the live stream, and we hope to see you on our future Connecting with Professional series. Bye.